Hi, my name is Clinical Clarness and you're watching the video on how to interpret the clinical results of a patient who has been investigated on the Synoptophore. So far we've learnt about the instrument itself and how to go about assessing a patient on the Synoptophore. But I want to now delve more deeply into interpreting the clinical outcomes of a patient. To do this, we'll systematically go through each grade of binocular single vision that the Synoptophore assesses. So let's commence with simultaneous perception. You'll recall for simultaneous perception, we have slides that differ but are paired in a way that we can ask the question about whether in this particular instance the line is in the cage. So what we're seeking here is one of two things. One is, can the patient see the line and the cage at the same time? And then can they superimpose the line on top of the cage so that the line is in the cage? Now, if the patient can do those two things, then there's an indication here that simultaneous perception is present. The alternative is that they can't see one of the images. So as an example, if they can't see the line and the line is in front of the left eye, we have left suppression. Now, when you have suppression, what you want to do is ensure that that suppression persists through differing sized slides. So if you have a suppression response with foveal slides, this could indicate that all you simply have is central suppression. In this instance, if you then used a peripheral slide, the patient will be able to see both the line and the cage with the larger slides, because they do have subnormal binocular single vision and do have simultaneous perception. It was just that that lion was being projected specifically only on the fovea, and therefore, as it's centrally suppressed, the patient is not going to see that image. Okay, there is one other possibility as well, that the patient does have simultaneous perception. They can see the line in the cage at all times, but they cannot put the line in the cage. So as an example, let's say we have a patient with a right esotropia, and when you put the slides in, they see both the line and the cage. And you then ask the patient to move the line, which is in front of the right eye, until they have the line in the cage. And they attempt to do this by taking that horizontal deviation control and moving that slide forwards, but they can never actually get that line in the cage. And what they tell you is that at one point they see the lion to the right of the cage, and then all of a sudden they see the lion to the left of the cage, but they can never put the line in the cage. What that's telling you is the patient has no potential for binocular single vision and has no BSV. But the other thing it's telling you is that that point where the line crosses over from the right side to the left side, in this example, represents the fovea as interpreted by the patient. Okay, so we're moving from, in this example, nasal retina to temporal retina when we go from the right side to the left side. And the retinal point that does this, or divides the retina between temporal and nasal, is the fovea. Now, it could be the true fovea, it could be the pseudofovea, depending on whether ARC is present. So effectively, the patient telling you that the image crosses over at this particular point, you're actually getting a subjective indication of where the patient interprets their fovea to be. So despite the fact that you can't get the line in the cage, you are actually gaining information about the location of the fovea or pseudofovea. Now, during our testing of the patient with the simultaneous perception slides, we are going to determine the size of the deviation objectively and the size of the deviation subjectively. And through doing this, we're going to gain information about whether normal retinal correspondence exists or whether abnormal retinal correspondence exists. And the way we do this is we compare subjective and the objective response. And for normal retinal correspondence to be present, the subjective angle of the deviation will be the same as the objective angle of the deviation. What does this mean? Let's use again an example of a patient with a right esotropia of, let's say, 20 diopters. Now, when I did the cover test on the Synoptophore, I will have moved the horizontal handle forwards by 20 diopters and measured that the fovea is located at this position, and that's the size of the deviation. If I then ask the patient, is the line in the cage, the patient would say, yes, the line is in the cage. In other words, they're using the true fovea as the fovea. They don't have ARC. The subjective angle is 20 prism diopters, as is the objective angle. However, if objectively I found the deviation to be 20 prism diopters and placed the line at that location, and the patient said the line is not in the cage, then we have an issue. The patient doesn't perceive the true fovea as the fovea, and they will then move the horizontal handle until they tell me that the line is in the cage. And so what they're doing is they're moving the line to the pseudofovea in this instance. And therefore, effectively, you have the subjective angle not being equal to the objective angle. So in the presence of ARC, there will be a difference between the angle of deviation that you measure objectively and the angle of the deviation as measured by the patient subjectively. And you see here, the image to the right, we have a patient whose CIP is here and the fovea is here. Initially, as you begin, the line will be projected on CIP, and then you'll move the tube so that the image falls on fovea. Should the patient have normal retinal correspondence, the line will be in the cage at this time. However, in the example we have here, the patient sees the line in the cage here. So when the line is on 0, even though objectively the orthoptist is finding that there is a 20 prism diopter esotropia. Here we have abnormal retinal correspondence. There is a difference between the subjective angle, so the patient thinks that the line is in the cage at 0 diopters, and objectively you think it is at 20 prism diopters. Now, when we detect ARC on the Synoptophore, we can actually gain quite a bit of information about the ARC point. If we think about Worsfold lights and Bailey striated glasses, these tests only tell us information about whether ARC is or isn't present. But they don't necessarily give us the information about how far away the ARC point is from the fovea, is it on nasal retina, is it on temporal retina, etc. The Synoptophore can give us all that information. It can give us information about the angle of anomaly, which is the distance of the pseudofovea from the real fovea or the true fovea. It can give us information about where that pseudofovea is located, on what retina, nasal or temporal, and again, how far away it is from the fovea. It can tell us what the angle of diplopia is, and what the angle of diplopia is essentially how far away the diplopic image will be from the real image. And we can gain information about what we would expect if the patient is experiencing diplopia, whether it will be crossed or uncrossed. Okay, to do all of this, what we do is we draw Synoptophore diagrams, and these are slightly different to the projection diagrams we've been used to so far. And here I've given you an example of some results where we have a Synoptophore finding with correction. The objective angle is -5 diopters fixing left, and the subjective angle is +15 diopters. So we have a difference between objective and subjective, and we have ARC, and now we're going to go to the effort of calculating the angle of anomaly and finding the location of this pseudofovea. For the Synoptophore diagram, we'll depict the left eye on this side and the right eye on this side, and we will have an arc here that represents the angle of the deviation, and we'll have one for each eye. 0 is in the centre. All values for the left eye over here are minus, so if a patient has a negative or exo deviation, it will be represented on this side. If they have an ESO deviation, it will be represented on this side. For the right eye, the ESO deviation will be represented on this side, and the exo deviations on this side. Okay, for this particular case, we did the assessment fixing left. So what we do is 0 will represent the fovea of this eye, as it's been fixed and locked. And now we don't need to worry about this eye at all from here on in. What we now want to do is draw the objective and subjective responses of the right eye. The objective angle was -5 prism diopters. Now you recall from our discussion earlier that this represents where the true fovea lies. So you'll draw -5 prism diopters. So here we have -5, and we'll take the line and draw the location of the fovea on the right eye. And we'll label that as fovea of the right eye. Now the subjective angle is 15. Let's draw that. And we'll see that we're now in the plus region. We take the line from 15 prism diopters, draw it onto the retina here, and label this as abnormal retinal correspondence. This is where the pseudofovea is located. This is where the patient is telling me the pseudofovea lies. We would then take this synoptophore diagram and translate that into a free space projection diagram. So here we have the free space projection diagram. We have the left eye as the fixing eye, and so an image here would be projected onto the left fovea and projected back in space as being straight ahead. Now the image here would fall on the CIP, and we know from this synoptophore diagram that fovea is nasal to the CIP and the ARC is temporal to the CIP. And we could find out exactly how far the fovea is from the ARC point, and we could, or the fovea to the CIP or the CIP to the ARC from this projection diagram here. The thing we need to now ask ourselves is, what is the type of diplopia the patient is going to experience given the location of the fovea, the CIP and the ARC? And what we need to think about is, where is the CIP in relation to the ARC? Because the ARC is the pseudofovea, and in free space with both eyes open, this will act as if it is the fovea. So the CIP is nasal to the ARC point, in which case the patient will experience uncrossed diplopia. Okay, we can find out more than just that information. One is, we can find out the angle of anomaly. So what is the distance between the pseudofovea and the fovea? What we do is we subtract the objective angle, which is -5 prism diopters. Sorry, that should be prism diopters. Minus plus 15 prism diopters, which equals -20 prism diopters. And we can see this on the projection diagram. If we see here, the red line is or represents the fovea, the green line represents the pseudofovea, and the distance between those two is 15 plus 5. So we've got 20 diopters as the angle of anomaly. The other bit of information is that we get a sign here of minus, which indicates on what part of the retina the pseudofovea is expected to be. And when we draw it in free space, we can see that the CIP is indeed on temporal retina. So minus represents temporal, plus represents nasal. And here is the fovea. CIP is temporal to the fovea of the right eye. So should you draw a projection diagram that doesn't match the angle of anomaly, then you have an issue with something that you've drawn, because it should match. In terms of the angle of diplopia, well, it always relates to the subjective angle. The second image and how far apart it is will relate to the subjective angle, which is in this instance 15 prism diopters. So from this assessment, we're able to say that the angle of anomaly, the distance between the fovea and the pseudofovea, is 20 prism diopters. The pseudofovea is located on the temporal retina. The patient will have uncrossed diplopia, and the angle of diplopia is 15 prism diopters. Much more information than other tests that assess retinal correspondence. Let's do one more example. Here we have synoptophore with correction, objective angle plus 10 diopters fixing left, and subjectively the patient thinks it's at -3. Again, we'll fix the left fovea at 0, and we'll draw where the fovea and pseudofovea is located on the right side. So the fovea is at +10 and the ARC point is at -3. So in terms of the angle of anomaly, we have plus 10, the objective angle, minus -3, which means that we're going to add 3. And so the angle of anomaly is 13 prism diopters. It's plus 13, which means I expect the ARC point to be on nasal retina. And I can have a look here and I can see this is fovea, this is temporal retina, this is nasal retina, and indeed the ARC point is falling on nasal retina. Let's translate this now to a free space diagram. So here we have the patient and the CIP is sitting between the fovea of the right eye and the ARC point, just as we see here on the Synoptophore diagram. So in order to work out the diplopia, we now need to consider where is it in relation to the pseudofovea. It is temporal to the pseudofovea. Remember, the ARC point remaps the retina so that this now divides the retina between nasal and temporal. So this CIP is falling on temporal retina when the patient has both eyes open and the pseudofovea is operating as having the principal visual direction. And therefore, as a temporal retinal point, the patient will experience crossed diplopia. Okay, we now have an issue here. We have a patient who has an ESO deviation. Objectively, you found that the patient has a plus 10 prism diopter ESO deviation, which means if you were to cover test this patient, you would find an esotropia in free space. And the expected diplopia of a patient with an ESO deviation is uncrossed. But this patient is experiencing crossed diplopia. Why? Because of the pseudofovea, because of the location of the pseudofovea. It's now making that CIP fall on a temporal retina according to the cortex, which then makes that diplopic image project in the cross position. This is called paradoxical diplopia. Paradoxical diplopia means that the diplopia is not consistent with the deviation present. So when you have an ET, you have crossed diplopia, even though you're expecting uncrossed. And the only time you can have paradoxical diplopia is in the presence of ARC, because it's only an ARC point or a pseudofovea that can remap the retina such that the CIP now functions as if it's a retinal point on the other side of the retina that it actually is. So in this case, the CIP in reality is a nasal point if you take it from the true fovea, but it is a temporal point when you consider the pseudofovea. Finally, if we go back to the previous example, we'll find that that patient also had paradoxical diplopia. If we take a look at this patient, the objective angle is -5 prism diopters, which means they have an exodeviation, but the patient is experiencing uncrossed diplopia. So again, we have paradoxical diplopia where the deviation is an exo, so we're expecting cross diplopia, but the diplopia of the patient is uncrossed. It's paradoxical. And the reason this has occurred is because of the presence of ARC, and in particular, what's common between the two cases is that the CIP is between the ARC and the fovea. And as such, every time your CIP is located between those 2 points, you will end up with paradoxical diplopia. If, however, it is not between these 2 points, you should actually get consistent diplopia as expected for the deviation present. However, what we know is that the angle of diplopia obviously is not consistent with the angle of deviation. The diplopia experience and the separation of the images is dependent on the pseudofovea, not the fovea. So as an example, if you have a 25 diopter ET, generally you would expect the diplopic image to be 25 diopters away from the real image. However, it won't be. The distance between those two images will be dictated by the pseudofovea. Let's do one more example, and this time we'll map a suppression scotoma. So we've got a synoptophore result here, objective angle at +10, fixing right, and subjectively the patient can only see the cage from -15 diopters to +15 prism diopters. Now this time, because the patient is fixing right, we'll fix the right eye, so 0 falls on right fovea, and we'll do our projections on the left eye. So plus 10 will be where the left fovea is located. Minus 15 represents the border of the suppression scotoma on one end, and plus 15 represents the border of the suppression scotoma on the other end. And so the suppression scotoma is between those two borders, between the plus 15 and the minus 15. We can then translate this to a free space projection diagram. So here we have the patient fixing with the right fovea and the image falling on the CIP of the left eye. We establish from the Synoptophore diagram the CIP lies nasal to the left fovea, and the distance between those two is 10 diopters. So if we have a look here, this is 0 where the CIP is. The CIP is always at the 0 point, and 10 diopters away is the fovea. Okay, let's then transpose the suppression scotoma on this retina, and what we see is that for another 5 diopters beyond the fovea, we have the suppression scotoma continue. So beyond the left fovea, we have 5 diopters of suppression scotoma. And then beyond the CIP, we have another 15 diopters of suppression. So altogether, we have 30 diopters worth of a suppression scotoma. And so here we've mapped the suppression scotoma of the patient, and we can indicate to the surgeon that an undercorrection for this patient would give the patient no diplopia, and an overcorrection of no more than 5 prism diopters will keep the patient with single vision. Again, not binocular single vision, but they'll have single vision and won't have the complaint of diplopia. So the surgeon can safely undercorrect and overcorrect by, or up to I should say, 5 prism diopters. Moving on to fusion, we can have several responses with these slides as well. And you'll recall that these slides allow us to detect sensory fusion and motor fusion. And using these slides, the rabbit, if the patient has sensory fusion, they'll be able to fuse the rabbits into one. And if they have one rabbit that's fused, they'll see the flowers and the tail. So one rabbit with flowers and a tail. That depicts sensory fusion. If they have motor fusion, when we attempt to converge the tubes and diverge the tubes, we'll note that the patient can maintain binocular single vision. They can maintain a single rabbit with the flowers and the tail through convergence and divergence whilst making a fusion convergence or divergence movement. And in that way, we'll actually measure the fusion range, the break and the recovery. The alternative is that the patient shows sensory fusion but no motor fusion. What does this mean? It means that upon commencement, the patient can see one rabbit with flowers and a tail, which tells us they have sensory fusion. But as soon as you try to diverge or converge the tubes, the patient immediately develops diplopia, in other words, sees 2 rabbits, or they immediately suppress one of the images so the flowers disappear or the tail disappears. So this patient cannot maintain that fusion through a vergence movement. Okay, another alternative is that the patient describes superimposition to you. What superimposition is that they will see this slide or this rabbit on top of this rabbit. So they don't actually see one rabbit, they'll tell you that it appears to be 2 rabbits, one on top of the other. And one's holding flowers and one's got a tail. What that's telling you is that they have simultaneous perception. They can see from the right eye and the left eye, but they are unable to fuse the 2 images into one. Sensory fusion is absent. And given that sensory fusion is absent, they will not be able to depict or demonstrate motor fusion. So as soon as you go to converge or diverge the tubes, the patient will immediately have diplopia or see those images side by side. And lastly, the patient can have no sensory or motor fusion, which means as you move into this stage of assessment and you place the fusion slides into the slide holders, the patient will describe to you either seeing 2 rabbits or as seeing 1, and they'll either see the flowers, or the rabbit with the flowers, or the rabbit with the tail, depending on which eye they're suppressing. And finally, stereoacuity. There's only 2 possible responses here. Either they appreciate the disparity and have stereopsis, or they don't. So where they appreciate stereopsis, they will be able to accurately indicate whether these buckets or the base of the bucket is directed towards me or themselves, me as the examiner or themselves as the patient. So if the patient can accurately identify the disparity, they are considered to have stereopsis. If, however, they fail to accurately identify the disparity, then they're considered to not have stereopsis. And just a reminder that with the Synoptophore, we're not actually measuring the stereoacuity level. We're not recording the minimum disparity the patient can perceive. We're simply indicating, do they have stereopsis or don't they have stereopsis? Okay, that brings us to the conclusion of this video. Thank you for watching.